Well, this is the last video, the 5th video on enols and enolates. And I've had to cut the last video down to just discussion of Claisen condensation, wherein an enolate ion attacks an ester or a carbonate to give us a more stable anion, that happy face enolate ion. That's part of the Claisen condensation. That was not seen in aldol condensation. Remember, Claisen condensation has a weak base that drives Claisen condensation over aldol condensation. That was important to see. In this last video, we're actually not going to look at anything new as reactions go. We're going to just combine some old reactions that we've already seen. So, acetoacetic ester synthesis and malonic ester synthesis really involve two reactions that we've already seen. So the first one's going to be alpha alkylation, and the last is going to be decarboxylation. So these reactions are put back to back. When you have acetoacetic ester synthesis, you're making ketones. The name kind of is misleading. Malonic ester synthesis, we're making carboxylic acid. What reactions are we using for these two reactions? Alpha alkylation followed by decarboxylation. So let's finish with this discussion of these two, and then I'll add in, because we have time, a little discussion of what you might hear or see as Robinson annulation. It's not in my notes. It's not going to be involving a new reaction. It's just going to be two reactions put back to back. Let's look at acetoacetic ester synthesis. When you see this name, you need to remember that you're going to a ketone. That's what you're making. Is not an acetoacetic ester. That's what it seems to say, but you're making a ketone. So, what I want to do is go ahead and that's going to pick up right at this point. We're going to have an acetoester as the starting point for this reaction. But we could have made it to kind of to go back. This will be the starting point for this reaction. But to go back, we could have done, and I have just a little fun with this, a two-step dip and twirl in our sort of dance, country dance. We're going to put this reaction, this reaction, we're going to have it as part of a country dance. So if you don't mind, this will be the starting point for acetoacetic ester synthesis, is to start at this point. But we could go back and say, how could we have made this beta ketoester, the beta ketoester that is the starting point for acetoacetic ester synthesis? Well, we could have taken and done Claisen condensation. We could have added a strong base, sodium methoxide, again not hydroxide, we don't want to make carboxylates, and then we could have simply worked up with acid once this reaction is done. So we know the methoxide makes an enolate in the first step. We attack, kick off a leaving group. This carbon is now right here. Let's highlight it this way. That carbon is now attached as the new nucleophile, the enolate ion. We would have torn off, really, the second proton as the methoxide comes back in and makes the happy face enolate ion. But I'm not drawing that because I've worked it up in acid and we've put the protons back on to give us a neutral structure. So this is just Claisen condensation to get us to the beta ketoester that is the starting point for acetoacetic ester synthesis. So let's go. Acetoacetic ester synthesis. First thing we have to do, I'm calling it the dip here, is alpha alkylation. So we have to notice this alpha position has in the product here a cyclobutyl ring, I guess, that it's part of. So how do we make that? Well, we got to count the carbons, 1, 2, 3, and propose that what I have is a dihalide where I have 1, 2, 3 carbons within that dihalide. So this would be a 1,3-dibromopropane. But of course I can't attack as is. This is not ready to attack the carbon. So I need to add not sodium hydroxide and not just one equivalent, but I need to use sodium methoxide, because if I use hydroxide, this ester will go to carboxylate, saponification, and we're done. We're not going anywhere. But if I use sodium methoxide, nothing new would be formed if he attacks as a nucleophile, but he can act as a base. Rip off the proton, allow for attack of one of these, and then if we use two equivalents of this, so I'm going to just put in my note here, two equivalents of this sodium methoxide added along with the alkyl bromide. Now I do want to point out, we may have trouble if this started to react with the alkyl halide. We may have to use a bulky strong base to rip that proton off. We may need to use something that's bulky so it doesn't attack directly the alkyl halide that we want to have attacked by the alpha carbon as a enolate. So we can run that reaction by adding again two equivalents of a strong base, adding in after that, but still part of the reaction solution, this 1,3-dibromopropane. That would give us our product. And then from this point we can go ahead and add, now that we have our alpha alkylation done, check, we have these groups added. Now we can run our decarboxylation. And I'm going to go ahead and add just water, a lot of acid, and some heat. We know that would allow for acid catalyzed hydration of the ester. In other words, after just having water with acid, we could replace this with an OH. And then by adding heat, we could drive off CO2 and have our final decarboxylation product. Wherein again, if you don't remember from the last video, this ester is converted to a carboxylic acid. A proton would replace this methyl group, and this can come off as CO2, and that proton that would be here would go back to the alpha position. So this is our decarboxylation. We've added just water, lots of it, and acid and heat to drive that decarboxylation. And this is our final ketone. And that's what we were expecting. So we can make a lot of different types of ketones where we have different alkyl groups at this position. We just chose to make a cyclobutyl group off of this alpha position. Let's look at the last one. It has the same sort of combination, or it has the same combination of reactions, alpha alkylation, decarboxylation. But we're going to make various carboxylic acids. Why? Because we're not starting with a beta ketoester. We're starting with a malonic ester. We have two esters functionalities bridged by this CH2 group. Now we could have used, guess what? We could have used, just like we did before, we could have used Claisen condensation, where we have an ester and a carbonate reacting to go through this reaction to give us a starting point as a malonic ester. This is a malonic ester. So how do we go through the malonic ester synthesis? So again, we're not forming a malonic ester in this malonic ester synthesis. It's a carboxylic acid we'll be forming. Well, let's go ahead and look at this left side where we have alpha alkylation of this carbon through the combination of KOR and, again, a difunctional halide, because they're showing a ring structure off that carbon at the alpha position, and then our decarboxylation. So let's go through this left side first. We should notice that if we add KOR to this malonic ester, we're going to need two equivalents. How do we know that? Because we have replacement of two protons with carbons. So we're going to need two equivalents, just like before. That could be a problem if these two start to react, because even if I add two equivalents of KOR initially to the malonic ester, and then add the 1,4-dibromobutane, there is still going to be some amount of KOR floating around in solution that has not yet reacted to take the second proton away. So there could be some reaction here that we may need to worry about. If that was a concern, we could make this a bulky base, so it would not act as a nucleophile. So either way, we, with those two equivalents, can sequentially make an enolate, have it attack one of these carbons to kick off a bromide. Another equivalent takes off the last proton. The enolate attacks from the other side, and we get a ring structure off that alpha carbon. That's our alpha alkylation that we've done just twice, like we did on the last slide. We don't have to do it twice. I'm just showing this as an example. Well, now we finish with our saponification, working it up in acid and adding heat. So this is a little different from the choice we made here. Acid with a lot of water, we can hydrolyze this in acid catalyzed conditions and add the heat and get the same thing, decarboxylation. We can also do it by just adding equivalent amount of KOH to convert both these sides to carbonates, add acid to convert both these sides to carboxylic acids, but only one of the carboxylic acid groups can go away. You can't take away both, because if we need a carbonyl, if the proton off of these oxygens, so I'm just going to go ahead and write it after this step, we would lose the R groups and have H's there. After this first two steps in the reaction, KOH, two equivalents with acid, we'd have carboxylic acids. But there is an issue. We can't have the proton ripped off. We have to have, the proton oriented towards this carbonyl in order for CO2 to come off. So once this comes off and we have the carboxylic acid left over on the left side, there's nobody to take this proton so that we can lose CO2 from the left side. So you can only lose one of these two carboxylic acids hanging off this carbon. So we're going to just take the one on the right. We're going to say this proton was picked up by this oxygen and then delivered back to the alpha position through an enol to keto tautomerization. So only lose one side to CO2. So that's the decarboxylation, because that's driven by heat. This proton that would be sitting here is oriented or tethered by hydrogen bonding to this oxygen. Then when we heat it, it goes to that, and then we have a transformation from enol to keto tautomer. The proton ends up at this carbon. So that's the malonic ester synthesis to give us our carboxylic acid, and where we've just, again at the alpha position, done some alkylations to give us a particular type of carboxylic acid. Alright, and we already touched on, to make this malonic ester, we would have used a carbonate and an ester and gone through a Claisen condensation. Right, there's one last reaction I just want to show as we finish up our discussion of enols and enolates. It's called the Robinson annulation. You need to know that this is a conjugate addition, or a Michael addition, because we're going to use a enolate ion to attack the conjugate position, followed up by an aldol condensation, an intramolecular one. So intramolecular. That's an important note. This aldol condensation will happen intramolecularly. So let's go ahead and do the conjugate addition using an enolate ion. So that's really a Michael addition. So we're going to take the NaOH, and we don't have any concern for tunces or the carboxylate. There's no class 1 carbonyl here. This is a ketone, this is a ketone. So let's just go ahead and make an enolate ion. And this side will be favored because we have resonance, the localization of the negative charge, not only into the carbonyl, that's the enolate, but if we put the negative here, it can get into the benzene ring. If we put it here on this side, it can't. So we're going to favor enolate ion formation on this side. We're then going to attack the conjugate position. I'm going to need to use a little bit of this in water, and I'll explain why here in a little bit. So we're going to add this catalytic amount with some amount of water as a proton source. What I would get then, as we look to this reaction, I would get attack of this carbon through the alpha position. So I'm going to number these 1, 2, 3, 4, so I don't lose anybody. So 1, 2, 3, and the oxygen would be 4. And it's going to have a negative charge. We're going to have a double bond between 2 and 3. And off of 3, I still have that methyl group. I just flipped it over. Okay, and I still have the benzene ring down here. Alright, so now we're needing that water to give us just a little bit of an acidic proton so we can grease things up, get to the enol, and have the tautomerization back to the keto form. So I'll show the enol one more time. You've seen this already on different video, but we can say the enol formed here would tautomerize very quickly. Yes, I should have a double-headed arrow. Would tautomerize very quickly. It's reversible, but very much favors the ketone. Alright, so in the end, what we've basically done is erased that carbon-carbon double bond here in the enone that we attacked, the conjugate position. With the enolate on, we basically erased that pi bond, and we just put everything back together again. This is our Michael addition product, because we attacked a conjugate position. 1, 2, 3, 1, 2, 3. We attack the conjugate position using an enolate ion formed from the ketone shown. So this is our Michael addition product, but we're not done yet. Now what we're going to do is follow it up. This is what's special, Robinson annulation, meaning a ring-forming reaction. We're going to make a ring through an aldol condensation. So we have to remember what aldol condensation is. We have loss of water, that's the condensation part, and we, on our way, I guess, to that condensation product, go through an aldol. Aldol is formed, but it goes on to the enone. Aldol condensation requires that we have 2 alpha protons that are lost. So we can look at how we could form a condensation product by going to the alpha positions. So we could have just this potential 2 protons here. This is out. We cannot go aldol condensation by having this attack anybody, because this alpha position only has 1 proton. So we have kind of choices A here. Here we have at 2, B, and we have C. So those are starting points. Alpha positions that have 2 protons that, if we use that alpha position to attack a carbonyl intramolecularly, we could potentially get the aldol condensation product. So let's look at our A position. That would have to attack this carbonyl. Again, it has to be intramolecular. So 1, 2, 3, 4, 5, 6. It looks good, but be careful. You're going to have what's called a bridging carbonyl. The new ring formed would involve a bridgehead carbonyl, meaning this carbonyl would connect or would be a part of that new 6-membered ring. We don't want to use that position. It's out for not the reason we'd have a bad ring, it's just that that ring that's formed would involve a bridgehead carbonyl. That may not be very stable. What about 2? Well, if 2 is used to make an enolate ion, the only carbonyl it can attack, it's not this one, but this one over here. That'd be a 1, 2, 3, 4-membered ring if this carbon, made negative, would attack this carbon. But if we use C here, C, we're not going to have a bridgehead carbonyl because this carbonyl is already part of a ring. It would be part of the new ring. 2 rings and a bridgehead carbonyl. That's not good. This carbonyl is not part of a ring. Not part of a ring. Use this for an enolate ion, have it attack this carbon, and we would have a new 6-membered ring, 1, 2, 3, 4, 5, 6, where this is not part of an existing ring. Alright, so let's do it. Let's take 2 protons off this carbon and connect it through a double bond to this carbon, because that's what we get when we have aldol condensation is we get water lost, where the oxygen for this water comes from the carbonyl that we attack, and the 2 hydrogens come from the carbon we use for the attack. So numbering, I'm going to put new numbers to this, we can build the structure. 1, 2, 3, 4, 5, 6. That's going to be my carbon 1 here. It's going to be double bonded to 6. And let's just go backwards. We have our 5 right here. 4, nothing off of that. 3, 2 has that carbonyl still tethered to it. So this is now our aldol condensation product, also known as an enone, because we made the ene here, and it's part of now a conjugated system, the enone, ketone, enone. So that's our product. Now we might have, just interesting, since we still have the KOH floating around, or sorry, the OH anion floating around in aldol condensation, we may see these protons, I guess at position 5, we may see that favorably ripped off, because if we did, we'd have a lot of resonance delocalization. So that may help drive this reaction for this particular Robinson annulation. Well, that's it. I guess we've covered, looking back at the starting point, we've covered acetoacetic ester synthesis was the combination of alpha alkylation decarboxylation to make ketones, and malonic ester synthesis, which same 2 reactions were put back to back to make carboxylic acids. And we just went ahead, since we had time, and covered Robinson annulation. Thanks a lot. Bye-bye.